The essential requirements for long-term information storage are: it must be possible to store a very large amount of information. Information must survive termination of process using it. Multiple processes must be able to access information concurrently. Disks are used to store files. Information is stored in blocks on the disks. It should be possible to read and write blocks. Magnetic disks provide bulk of secondary storage of modern computers. Drives rotate at 60 to 250 times per second. Transfer rate is the rate at which data flow between drive and computer. Positioning time or random access time is the time to move disk arm to desired cylinder, seek time, and the time for desired sector to rotate under the disk head, rotational latency. Head crash results from disk head making contact with the disk surface, resulting in bad sector. Disks can be removable. Drive is attached to computer via input-output bus. Buses vary, including EIDE, ATA, SATA, USB, fiber channel, SCSI, SAS, Firewire. Host controller in computer uses bus to talk to disk controller built into drive or storage array. Moving head disk mechanism is shown here. We have several plates, and on each plate we have a read-write head on both sides. These are called arms. They are connected to arm assembly. As the arm assembly moves, there is a spindle to which the platters are connected, and the plates are rotating together with the spindle. On the surface of the platters, we have tracks. If we consider all the tracks at the same position on each platter, this is resulting in a cylinder. Tracks are divided into parts, which are called sectors. As the arm assembly moves, the track number changes, and as the spindle rotates, the sector under the read-write head is changing. The diameter of platters range from 0.85 inch to 14 inch historically. Commonly, 3.5 inch, 2.5 inch, and 1.8 inch are used. The capacity range from 30 GB to 3 TB per drive. Performance is affected by transfer rate. While the transfer rate theoretically is 6 GB per second, the effective transfer rate is about 1 GB per second. Seek time ranges from 3 milliseconds to 12 milliseconds. 9 milliseconds is common for desktop drives. Average seek time measured or calculated based on 1/3 of tracks. Latency based on spindle speed, which is calculated as 1 divided by revolution per minute divided by 60, which is equal to 60 divided by revolution per minute. The average latency is half of the latency calculated here. Here there is a table according to the spindle speed given in the first column, and the average latency calculated according to the spindle rate using this formula is given in the second column. The access latency is the average access time, which is equal to average seek time plus average latency. For example, to transfer 4 kilobyte block on a 7200 RPM disk with a 5 millisecond average seek time and 1 gigabyte per second transfer rate with a 0.1 millisecond controller overhead. Find out average input-output time. Average input-output time for 4 kilobyte block is given as average access time plus transfer time for 4 kilobyte block plus controller overhead. Average access time is average seek time plus average latency, and average latency is 1/2 latency, which is equal to 1/2 60 divided by RPM. So it is equal to 1/2 60 divided by 7200, which is equal to 4.17 millisecond. Average access time, average seek time plus average latency, which is equal to 5 millisecond as given here as the average seek time plus 4.17 millisecond as the average latency calculated in the previous step. The transfer time is equal to amount to transfer divided by the transfer rate. Amount of transfer is given here as 4 kilobyte. Note that B stands for byte and small b stands for bit, and 1 byte is 8 bits. So to convert this information into bit, 4 kilobyte multiplied by 8 bit per byte, which is equal to 32 kilobit, which is equal to 32 multiplied by 1024. This stands for kilo and bit. And the transfer rate is given here as 1 gigabit per second. So the transfer time is calculated as 4 kilobyte divided by 1 gigabit per second, which is equal to 0.031 millisecond. Therefore, average input-output time for 4 kilobyte block is equal to 9.27 millisecond, calculated here, and 0.31 millisecond, calculated at this step. And if we sum them up, it results in 9.301 millisecond. The first commercial disk drive is developed by IBM in 1956. IBM RAMDEC computer included the IBM Model 350 disk storage system, shown here, which has 5 mega characters capacity. Each character is 7 bits, and 50 of 24-inch platters. The access time is less than 1 second. Solid-state disks are another kind of secondary storage. They are non-volatile memory used like a hard drive. There are many technology variations. They can be more reliable than hard disks, more expensive per megabyte, may have shorter lifespan, they have less capacity but much faster. Buses can be too slow, so connect them directly to the PCI, for example. There is no moving parts, so no seek time or rotational latency is observed. Magnetic tape was early secondary storage medium. They are evolved from open spools to cartridges, relatively permanent and holds large quantities of data. Access time is slow. Random access about 1,000 times slower than disk, mainly used for backup, storage of infrequently used data, transfer medium between systems. They kept in full and won't or re-won't past read-write head. Once data under head, transfer rates comparable to disk. It is about 140 megabyte per second and greater. The typical storage capacity is 200 gigabyte to 1.5 terabyte. Disk structure. Disk drives are addressed as large one-dimensional arrays of logical blocks, where the logical block is the smallest unit of transfer. Low-level formatting creates logical blocks on physical media. The one-dimensional array of logical blocks is mapped into the sectors of the disk sequentially. Sector 0 is the first sector of the first rack on the outermost cylinder. Mapping proceeds in order through that track and then through the rest of the cylinders from the outermost to innermost. Logical to physical address translation should be easy, except for bad sectors and non-constant number of sectors per track via constant angular velocity. File systems. Think of a disk as a linear sequence of fixed-sized blocks and supporting two operations. 1. Read block K. 2. Write block K. The questions that quickly arise are: how do you find information? How do you keep one user from reading another user's data? How do you know which blocks are free? Use file system as an abstraction to deal with accessing the information kept in blocks on disk. Files are created by processes and there are thousands on a disk. Files are managed by the operating system, which structures them, names them, and protects them. The two ways of looking at file system are user point of view. How do we name a file, protect it, organize the files? Implementation point of view. How are they organized on a disk? We will start with user and then go to implementer. File systems, users' point of view. Users are interested in files, naming them, their structure, types, access, attributes, and operations. For directories, if they are single level, hierarchical, the path names, and operations. A file is stored in a contiguous logical address space. The types of files are data, which may be numeric, character, or binary, and also programs. The content of the files are defined by the files creator. There are many types. Consider text file, source file, executable file, etc. In file naming, 1 to 8 letters plus a 3-letter extension is used in all previous operating systems. In Unix, size of the extension is up to the user. FAT 16 and 32 were used in first Windows systems. Latest Windows systems use native file system, which is NTFS. All operating systems use suffix as part of name. While Unix does not always enforce a meaning for the suffixes, DOS does enforce a meaning. Some typical file extensions are given here. The extension is in the first column, then comes meaning in the second column. .bak is extension for backup file. .c is for C source program. .gif is computer graphical interchange format image. .hlp is for help files. .html stands for World Wide Web Hypertext Markup Language Document. .jpg still picture encoded with the JPEG standard. .mp3 music encoded in MPEG Layer 3 audio format. .mpg movie encoded with the MPEG standard. .o object file, it is compiler output, not yet linked. .pdf portable document format file. .ps PostScript file. .tex input for the text formatting program. .txt general text file. .zip compressed archive. The file structure may be byte sequences. This provides for maximum flexibility. Anything can be put inside. Unix and Windows use this approach. Another structure is fixed length records, and yet another one is tree of records. They use key field to find records in the tree. These are also called index files. Three kinds of files are given in this figure. In A, byte sequence is shown. In B, we have record sequences. Each record is made of fixed number of bytes, and this is a tree structure. In this example, notice that each node has 4 link fields and 3 data fields. The link field here between ant and fox points to another node which is containing cat, cow and dog, and this verse comes after ant and before fox in a dictionary. File types. Some Unix files are as follows. Regular files contains user information, directories, character special files which model serial input-output devices, for example, printers, and block special files. This model disks. The regular files are ASCII or binary. ASCII consists of lines of text. They are printable and they can use pipes to connect programs if they consume ASCII. And they can be used as pipes to connect programs if they produce and consume ASCII. Binary file types. 2 Unix examples of binary file types are executable and archive. For the executable files, there is a field which identifies file as being executable. And archive files, they are compiled but not linked library procedures. Every operating system must recognize its own executable. In this figure, binary file types for early versions of Unix is given. Here in part A, an executable file is given. Here, the magic number identifies it as an executable file. Then there is information about text size, data size, BSS size, symbol table size, entry point, etc. And also flags. This part is called header, and also there is text whose size is given here, data, relocation bits, and symbol table. In part B, an archive file is given. These are the library procedures compiled but not linked. In the header, we have module name, date, owner, protection, and size. And we have object module, and there are several header and the corresponding object module. Header, object module, etc. If sequential access is used for file access, the reader starts from the beginning and can skip around. This corresponds to reading from magnetic tape. Random access, it starts where you want to start. It came into play with disks necessary for many applications, for example, airline reservation system. File attributes, which are the metadata for the files. It has name, which is the only information kept in human readable form. Identifier, a unique tag, number, identifies file within file system. Type, this is needed for systems that support different types. Location, pointer to file location on device. Size, current file size. Protection, controls who can do reading, writing, execution. Time, date, and user identification. These are data for protection, security, and usage monitoring. Information about files are kept in the directory structure, which is maintained on the disk. There are many variations, including extended file attributes such as file checksum. These are the information kept in the directory structure. Some possible file attributes are given in this table. The first column corresponds to the attribute and the second column is meaning. The attribute protection shows who can access the file and in what way. Password is needed to access the file. Creator, ID of the person who created the file. Owner, current owner. Read-only flag, 0 for read-write and 1 for read-only. Hidden flag, 0 for normal and 1 for do not display in listings. System flag, 0 for normal files, 1 for system file. Archive flag, 0 for the files that has been backed up and 1 for the files needs to be backed up. ASCII binary flag, 0 for ASCII file, 1 for binary file. Random access flag, 0 for sequential access only, 1 for random access. Temporary flag, 0 for normal, 1 for delete file on process exit. Log flag, 0 for unlocked, non-zero for locked. Record length, number of bytes in a record. Key position, offset of the key within each record. Key length, number of bytes in the key field. Creation time, the date and time the file was created. Time of last access, the date and time the file was last accessed. Time of last change, the date and time the file was last changed. Current size, number of bytes in the file. Maximum size, the number of bytes the file may grow to.